Hi folks, uh, in the last short video I discussed with you isolated version of a switching power supply topology, which is called the half-bridge converter. And in half-bridge converter we saw that the maximum voltage stress on the transistors was only VDC instead of 2 VDC, which was in the forward converter and the push-pull converter. And also we saw that the flux imbalance problem in the half-bridge converter was not that severe as was in the case of forward converter and the push-pull converter. And to cater the flux imbalance problem in the half-bridge converter, we used a small blocking capacitor. In the today's short video, I will discuss with you another switching power supply topology, which is also a isolated version, and it is called the full bridge converter. As the name suggests, in the full bridge converter there are two phase legs of transistors. I mean one phase leg consisting of two transistors connected in series, normally in the form of MOSFETs, and the other phase leg also consisting of two transistors in series, which are also normally two MOSFETs. And the primary winding, one point is connected to the middle of the one phase leg, and other point of the primary winding is connected to the other phase leg's middle point. And the flux imbalance problem is not that severe, and to cater the flux imbalance problem we use a small blocking capacitor, as we use in the half-bridge converter. I mean whose one point is connected to the middle of one phase leg, and other point of the blocking capacitor is connected to that side of the primary winding. The maximum voltage stress on the full bridge converter is also VDC instead of 2 VDC, as was in the case of forward converter and the push-pull converter. So we can use full bridge converter in those scenarios also where the mains voltage is 440 volt AC. As we saw that to cater the flux imbalance problem, we utilized a small blocking capacitor. However, this blocking capacitor should not be sized of too much high capacitance value, because then it will rob or steal the voltage from the primary winding. And to get the desired output or maximum output power at the minimum input voltage range, the maximum on time of the diagonally conducting MOSFETs would increase more than 50%. And if it is increased more than 50%, then the shoot through can occur on that phase leg, and which can destroy the MOSFETs and hence the power supply. So we normally calculate the blocking capacitor such that it rob or steal the voltage from the primary winding no more than 10%. As the voltage on the primary winding is VDC instead of half VDC, and as in the case of the half-bridge converter, so we can get double the power from the full-bridge converter as compared to half-bridge converter. And we utilize full-bridge converter where the output power is 1 kilowatt or above that. As an example, in the daily life, you see the uninterruptible power supplies which are configured in the full bridge converter. So full bridge converter is a very versatile converter, and it is, as I told you, that it is used where the power demand is 1 kilowatt or above 1 kilowatt. And we also saw that to cater the flux imbalance problem, we utilized a blocking capacitor. and braking capacitor is needed because of the storage times which is inherent in the BJT. If we use BJT as a phase legs, or the slightly different on voltage drafts of the MOSFETs, we use MOSFETs as a phase legs. So this was today's short video. So stay connected and thank you very much.